A simple cylinder of boiling water eventually reshaped factories, transport, cities, and the global economy. Before steam, most mechanical work depended on muscles, animals, wind, or flowing water.
Water wheels were effective, but rivers decided where factories could operate and how much power they received. Growing towns demanded more coal, forcing miners deeper into the ground that constantly filled with water. Flooded shafts closed valuable mines because existing pumps could not remove water quickly enough.
Horse-driven machinery consumed land, food, and labor while delivering only modest power underground.
Heating water creates expanding vapor, turning stored fuel energy into pressure that can push objects.
Cooling steam reverses the process, shrinking its volume and leaving a partial vacuum behind.
The breakthrough required more than steam. Inventors needed valves, cylinders, pumps, and reliable timing. Steam power emerged through centuries of experiments rather than one sudden moment of invention. Nearly 2,000 years ago, Hero described a sphere spun by steam escaping through bent nozzles. Reaction from the escaping jets produced rotation, proving that heated water could create motion. Hero's device demonstrated a principle, yet it could not deliver useful industrial power efficiently. Ancient craftsmen lacked the materials, manufacturing systems, and economic pressure needed for a practical engine. 17th century experiments made atmospheric pressure and vacuum understandable enough to become engineering tools. Once a vacuum formed beneath a piston, ordinary air pressure could produce a powerful stroke. Denis Papin explored using steam and condensation to move a piston inside a cylinder. Papin's safety valve addressed a central danger by releasing pressure before the vessel failed. Promising experiments remained isolated because full-scale cylinders, seals, and control systems were still unreliable. Economic pressure from flooded mines finally turned steam research into a practical engineering race. Thomas Savery patented a steam-powered pumping system in 1698 for removing mine water.
Savery marketed the machine as the miner's friend, promising relief for waterlogged workings.
First, steam filled a sealed vessel and displaced the air already trapped inside.
Next, cooling condensed the steam and created a partial vacuum inside the vessel.
Atmospheric pressure then pushed mine water upward through the suction pipe into the chamber.
Fresh steam pressure forced the collected water upward through a second pipe toward the surface.
Savery's pump avoided a piston, making the concept mechanically simple but physically constrained. Vacuum could raise water only from shallow depths, far below what many mines required. Greater delivery height demanded higher pressure from boilers that contemporary metalworking could not always contain. Weak joints and uncertain pressure control made early steam pumping hazardous as well as inefficient. Repeated heating, cooling, and pressurizing consumed large amounts of coal for limited pumping work.
Savery's design found limited uses, yet it rarely solved the deepest mining problem it advertised.
Nevertheless, Savery proved that continuous steam cycles could convert heat into practical pumping. The next breakthrough replaced pressurized water vessels with a piston driven by atmospheric pressure.
That new arrangement became the atmospheric engine, the first widely practical steam-powered machine.
Thomas Newcomen and John Calley combined practical metalworking, plumbing, and earlier steam ideas.
Their machines separated the power cylinder above ground from pumps operating deep below.
In 1712, a new common engine began pumping near Dudley, and demonstrated practical industrial power.
The towering structure converted a repeating steam cycle into long vertical strokes for mine pumps. Low-pressure steam filled the cylinder while the heavy pump rods lifted the piston upward.
The upward stroke prepared the cylinder for the engine's true power-producing event. Cold water injected into the cylinder condensed the steam almost instantly. Condensation left a vacuum below, creating a large pressure difference across the piston. Atmospheric pressure pushed the piston downward, which is why Newcomen's machine was called atmospheric. That working stroke raised pump rods and moved water toward the surface through staged pumps. After drainage and steam admission, gravity reset the beam for another power stroke.
Mechanical valve timing eventually allowed the engine to repeat its cycle without constant manual control.
A simple plug tree mechanism synchronized steam, injection, and drainage with the moving beam.
Using atmospheric pressure reduced boiler risk, but demanded heavy structures and large components.
Newcomen engines reopened drowned workings and made deeper coal extraction economically possible. Successful installations spread because mining districts urgently needed dependable pumping rather than perfect efficiency. Newcomen's appetite for fuel mattered less where low-cost coal sat beside the engine.
Every stroke reheated and recooled the same metal cylinder, wasting enormous quantities of steam. Most fuel energy disappeared because condensation occurred inside the working cylinder itself.
Decades later, a faulty model engine exposed that inefficiency to a young instrument maker.
James Watt encountered the Newcomen design while repairing a university demonstration model in Glasgow.
The model consumed surprising amounts of steam because its cylinder repeatedly lost heat. Careful measurements showed that cylinder cooling, not merely friction, caused the engine's waste. Watt asked whether condensation could happen somewhere else, while the power cylinder remained hot. His answer was a separate condenser, a cold chamber dedicated to collapsing exhaust steam. Separating the condenser allowed the working cylinder to remain hot throughout repeated strokes. Steam could now condense rapidly in another vessel without reheating the cylinder afterward. The colder separate chamber also produced a more effective vacuum for the next stroke. An air pump cleared condensed water and unwanted gases so the vacuum could continue. A surrounding steam jacket further reduced heat loss from the cylinder walls. Side by side, Watt's arrangement used the same basic piston idea with far less wasted heat. Watt patented his method for reducing steam and fuel consumption in 1769.
Matthew Boulton supplied the capital, workshops, and business organization needed to commercialize Watt's improvement.
Soho's manufacturing network turned experimental components into repeatable engines for paying customers. By 1776, successful commercial engines began demonstrating major reductions in coal consumption.
Their business model linked payments to measured fuel savings, making efficiency financially visible.
Lower fuel costs made steam power practical in industries far from cheap mine-mouth coal. Closing the cylinder allowed steam itself to act above the piston instead of open air. Watt's double-acting engine used steam to power both the upward and downward strokes.
Double action increased output and created motion better suited to continuous industrial machinery.
Factories needed rotating shafts, not merely the back and forth motion used by mine pumps. A competing patent complicated direct crank use, pushing Watt's team toward another solution. The Sun and Planet gear converted each beam stroke into continuous rotary motion. A massive flywheel stored momentum and reduced the pulsing character of reciprocating power. Rotary steam engines could now drive entire rooms of machinery from one central source.
Watt's parallel motion linkage kept the piston rod aligned while the beam travelled through an arc.
A centrifugal governor automatically reduced steam flow when engine speed rose too far. This mechanical feedback system regulated power long before electronic sensors or computers existed. Pressure diagrams helped engineers diagnose engines and compare performance using measured cycles instead of guesswork. Watt popularized horsepower as a practical way to communicate machine output to customers. Centralized power allowed manufacturers to coordinate many processes inside a single production system. Steam released factories from seasonal rivers and widened the geography of industrial production.
Textile mills used dependable rotary power to run larger numbers of machines for longer hours.
Steam increased iron production, while better iron enabled stronger boilers, cylinders, and machinery. Energy, materials, and manufacturing improved together, accelerating industrial change beyond any single invention.
Steam power encouraged production schedules governed by machines rather than weather and flowing water.
Greater output arrived alongside harsh workplaces, long shifts, and new forms of industrial inequality. Coal-fired steam concentrated pollution around industrial towns and altered urban health and landscapes.
Stationary Watt engines transformed factories, but transport required lighter machines with stronger pressure.
Watt distrusted high-pressure steam because weak boilers could fail with catastrophic force.
Improved materials and machining gradually allowed smaller boilers to contain greater pressure more reliably.
High-pressure engines used steam itself as the main driving force, increasing power relative to size. Cornish engineer Richard Trevithick pioneered practical high-pressure engines around the turn of the 19th century. Trevithick demonstrated that a compact steam engine could move itself rather than remain inside a building. Rails reduced rolling resistance enough for steam power to haul far heavier loads. In 1804, Trevithick's locomotive completed the first railway journey hauled by steam. The demonstration proved feasibility, although tracks and engines still required major improvement before widespread adoption. Advances in track, wheels, and boilers transformed isolated experiments into reliable railway systems.
Steamships delivered scheduled movement against currents and weak winds, reshaping inland and ocean transport. Steam transport reduced travel times and linked markets, resources, and populations across greater distances.
Higher pressures increased mobility and efficiency, but they also made boiler failures more destructive.
Defective materials, bad joints, overheating, and poor maintenance all contributed to explosions.
Engineers responded with better gauges, relief valves, operating procedures, and formal inspections.
Public failures pushed governments and professional bodies toward enforceable boiler standards.
Steam engines forced scientists to formalize relationships among heat, energy, pressure, and mechanical work. Thermodynamics explained why no heat engine can convert every unit of fuel into useful motion. Later engineers expanded steam through multiple stages and refined timing to extract more work. Steam turbines eventually delivered smoother rotation, at scales suited to electrical generation and large ships. Modern power plants often use advanced steam systems even when their heat sources differ completely. Steam technology evolved from mine pumps into a broad family of engines rather than disappearing.
No one person invented the complete steam engine. Each generation solved a different obstacle.
Practical steam power required reliable heat, controlled pressure, sealed motion, and useful mechanical transmission. At its core, the engine converts thermal energy into controlled movement through repeated pressure changes. That conversion expanded production and mobility, while also deepening dependence on fossil fuel and industrial systems. The steam engine emerged step by step until engineers learned to make heat move the world. The asteroid's first day was only the beginning. The extinction accelerated when sunlight itself began disappearing from Earth. Rock dust, soot, and sulfur aerosols entered the atmosphere together, but each would block sunlight in a different way. Fine dust scattered light, soot absorbed it, and aerosols reflected it. Different particles.
High-altitude winds spread the impact cloud across hemispheres, turning one crater into a planetary atmospheric event.
For many survivors, the next sunrise arrived weak, red, and unfamiliar. Daylight no longer behaved like daylight. Surface light fell sharply. Even places untouched by blast, fire, or tsunami began receiving less usable energy. Photosynthesis did not stop everywhere at once, but the energy entering ecosystems had already begun to fall. The crisis began at the bottom. When primary producers weakened, every consumer above them inherited the loss. Normal night still crossed the planet. Behind it came a darkness that did not end when morning returned. Impact winter was not a single dark afternoon. Its duration depended on how long dust, soot, and aerosols remained. Sulfur gases formed reflective aerosols that reduced solar heating, although the total sulfur released remains scientifically debated. States silicate dust, as meaning that the tillis meating to it low-range dust, low sunlight.
Soot absorbed light instead of reflecting it, potentially adding another layer of darkness to the developing winter.
Three mechanisms, scattering, absorption, and reflection, work together to cut the energy reaching Earth's surface. Scientists agree the impact caused severe dimming. The exact balance of dust, soot, and sulfur remains an active research. From orbit, Earth still received sunlight. The problem was how little of that light could penetrate to the living surface. Darkness was global, but not perfectly uniform. Latitude, clouds, and particle density shaped how much light survived. Light disappeared faster than heat. The sky darkened within hours, while the full cooling unfolded more slowly. Once incoming energy collapsed, global temperatures began falling. Land cooled rapidly, the oceans responded more slowly. This was impact winter. Darkness above, cooling below, and a shrinking energy supply connecting every ecosystem. Even the tropics lost warmth. Ecosystems adapted to stable heat, suddenly faced cold, dark. Seasonal rhythms were disrupted. Growth, migration, and reproduction no longer matched the conditions organisms had evolved to expect. In some regions, freezing conditions may have reached ecosystems with little protection from sudden cold. Climate models produce different numbers, but they consistently point toward abrupt, biologically dangerous cooling. Oceans stored heat longer than land, delaying the cold, but not shielding marine food webs from darkness.
Land and ocean cooled at different speeds, but both suffered from the same collapse in solar energy.
Cooling and dimming disrupted the water cycle, changing rainfall patterns already destabilized by impact debris and atmospheric chemistry. The atmosphere did not simply become colder, its circulation changed, redistributing clouds, wind, and precipitation. How long the darkest phase lasted remains uncertain, because different particles settled, reacted, and circulated at different rates. Darkness reduced food production. Cold increased biological stress. Together, they made recovery far more difficult. Plants survived the blast in many places, but surviving was different from growing under a darkened sky.
With less light, leaves produced less energy. Entire plants began running on stored reserves instead of new growth.
Roots, seeds, and underground tissues offered temporary protection, allowing some plant lineages to wait for better conditions. Forest decline removed more than leaves. It dismantled shade, nesting sites, moisture, and protection from predators. Burned landscapes faced a second crisis. Darkness and cold prevented rapid regrowth after the flames had passed. Ash and dust could reduce the little light that remained, adding physical damage to atmospheric darkness. Dead vegetation briefly fed decomposers, but recycled material could not replace a functioning photosynthetic system. Even where vegetation remained, it could be sparse, damaged, or nutritionally poor for large herbivores.
Extinction pressure grew because plants could not recover quickly enough to support the animals depending on them.
On land, the collapse moved upward. First plants, then herbivores, then the predators that depended on them. The ocean's most productive layer depended on sunlight. As that layer dimmed, the marine crisis began at microscopic. Plankton could survive brief darkness, but prolonged low light reduced growth and reproduction across enormous ocean areas. Marine productivity fell unevenly, but the global direction was clear. Less light meant less new biological energy. Some plankton faced a double burden: low light above and disrupted seawater chemistry around them. Dead plankton created a temporary food pulse below, but the deep ocean eventually received less fresh material from the surface. Ammonites survived earlier crises, but this collapse removed the productive marine system supporting their entire life cycle. Top marine predators were buffered from the impact only briefly. Their survival still depended on prey below them. The deep ocean avoided the worst surface heat and fire, but not the slow loss of food produced above. Coastal ecosystems faced both physical destruction and the global decline in sunlight-driven productivity. The marine extinction was also bottom-up. Microscopic producers failed first, then larger animals followed. Many non-avian dinosaurs probably survived the first day. The longer crisis was finding enough energy to remain alive. Large bodies required large, reliable food supplies. Impact winter made that ecological requirement increasingly impossible. Migration could escape a local fire or drought. It could not easily escape a planet-wide collapse in productivity. Water remained available in many places, but ash, sediment, and habitat damage made dependable resources harder to find. Extinction is not only about adults dying. It can begin when populations stop replacing themselves. Young animals face the same darkness and cold, with smaller reserves and complete dependence on damaged ecosystems.
Body size shaped risk. Large animals needed more energy. Small animals could survive on less and hide more effectively.
For large dinosaurs, the problem was not one missed meal. It was sustained scarcity across weeks and months. Starvation propagated through the ecosystem, turning plant failure into animal decline and then predator collapse. Non-avian dinosaurs were not defeated by one weapon. They faced a system-wide failure they could not outlast. Predators experienced the crisis one step later, but prey loss ultimately reached them with equal force. Carrion created a short-lived resource pulse, but dead animals could not sustain predators indefinitely. In the Nentry demand and Milsing donations and subsicitions to the Cotramitsa system. Syncopations, the same ecological logic operated at sea. Top predators could not survive after their prey base disappeared. Specialists were vulnerable when one essential resource vanished. Generalists could sometimes redirect their diets. Ecological redundancy mattered. A web with alternatives could bend where a narrow chain simply broke. Post-impact abundance could be deceptive. A burst of carrion was followed by a much longer period of scarcity. The longer darkness persisted, the more survival depended on reserves, low energy needs, and adaptable behavior. Small size did not guarantee survival, but it reduced several risks at once: food demand, exposure, and recovery time. Extinction was selective, not random. Biology, geography, and chance combined to decide which lineages crossed the boundary. Burrows reduced exposure to heat, cold, fire, and falling debris, 4 immediate and 1 small refuge. Freshwater systems offered shelter and stored organic matter, buffering some survivors from immediate food collapse. Water and sediment softened temperature extremes and protected organisms from some of the surface chaos. Detritus-based food webs could continue using dead organic matter after fresh plant growth collapsed. Fungi helped recycle dead material, supporting small food webs where living plants had become scarce. Seeds could wait. Dormancy allowed some plants to survive conditions that active growth could not tolerate. Insects linked seeds, fungi, and detritus to small survivors, keeping some food pathways active. Small mammals combined shelter, flexible diets, and modest energy needs, traits well suited to a damaged world. Some bird lineages may have benefited from small size and seed-based diets, although survival differed among groups. Low energy demands and aquatic refuges helped crocodilians and turtles survive conditions that eliminated many larger competitors. Birds were dinosaurs too. The extinction erased non-avian branches, while a few avian lineages survived. Ground-level feeding may have helped some birds after forests collapsed, but the evidence remains incomplete. Flight alone was not enough. A flying animal still needed food, shelter, and a functioning place to land. Dietary flexibility allowed some survivors to switch resources as familiar food chains disappeared. Smaller survivors could rebuild populations faster, but only if enough food and shelter remained. Mammals survived not because they were superior, but because many were small, flexible, and sheltered. Nocturnal habits may have made darkness less immediately disruptive for some mammals. Energy-saving states may have helped some small animals, although direct evidence for specific behaviors is limited. Freshwater refuges repeatedly appear among surviving groups, suggesting these systems buffered several forms of stress. No single trait guaranteed survival. Outcomes emerged from combinations of biology, geography, timing, and the extinction is preserved worldwide as a thin boundary separating the Cretaceous from the world that followed. Soot and impact dust in boundary sediments record the atmospheric material that spread around the planet. Iridium and impact glass identify the event's extraterrestrial source and its global reach. Climate proxies preserve abrupt environmental change, supporting a world that became darker, colder, and less productive. Fossils show abrupt biological turnover. Many dominant groups disappear, while a smaller set of survivors remains. The post-impact fern spike records pioneer plants colonizing landscapes where mature forests had vanished. Some records suggest increased fungal activity after the impact, but the pattern is not equally clear everywhere. Marine microfossils record a sharp crash in plankton diversity, and productivity at the boundary.
Plant fossils record severe ecological disruption, although the exact pattern varied from region to region.
Models explain mechanisms. Rocks test them. The strongest conclusions emerge where both lines of evidence agree. Weeks after impact, darkness and cold continued, while survivors depended on stored food, detritus, and protected habitat. The longer the veil persisted, the more temporary advantages became exhausted. Eventually, particles settled and reacted out of the atmosphere, allowing sunlight to begin returning. More sunlight did not instantly restore ecosystems. Food webs had already lost species, structure, and biological memory. Dust, soot, and aerosols did not disappear together. Their different lifetimes shaped the pace of recovery. Chemical disruption outlasted the darkest sky, continuing to stress soils, lakes, and oceans. Recovery began with opportunists, able to colonize damaged landscapes, not with the return of old forests. Ferns expanded quickly in many regions, marking recovery, while also revealing how completely forests' early recovery ecosystems were simpler, less diverse, and built around the survivors that remained. Survivors eventually expanded into emptied ecological roles, but rebuilding complex ecosystems took far longer than. When the sun returned, it illuminated a planet that was warmer and brighter, but biologically transformed. Sunlight returned, but non-avian dinosaurs did not. Their ecological world had already collapsed beyond recovery. Mass extinction created ecological vacancies, changing which lineages would shape the future. Mammals did not instantly dominate, but surviving lineages later diversified into opportunities created. Every living bird is evidence that one branch of the dinosaur family survived the winter. The asteroid did not finish the extinction in seconds. It triggered a chain of planetary failures. The decisive weapon was not the crater alone. It was the collapse of the systems connecting sunlight to life. Complex food webs can be powerful in stable worlds, and dangerously fragile when their energy source disappears. The year the sun disappeared did not erase all life. It decided which lives would inherit the planet. The asteroid opened the crisis. Impact winter finished the dinosaur world and made the modern one possible. For more than 2,000 years, people have searched for a city that may have existed only inside one man's story. Every surviving description of Atlantis begins with two dialogues written by the Greek philosopher Plato. Plato said the story reached Greece through Solon, who supposedly heard it from Egyptian priests. But no Egyptian document confirming Atlantis has ever been found, leaving the chain dependent on Plato's own account. Plato placed Atlantis 9,000 years before Solon, far earlier than any known complex city described in his story. His Atlantis was built in rings, circular canals, bridges, harbors, walls, and a monumental center. It was described as wealthy, technologically impressive, and powerful enough to dominate much of the known world. Plato placed Atlantis beyond the Pillars of Heracles, usually identified with the Strait of Gibraltar. That single phrase moved the search from the Mediterranean into the Atlantic, and eventually across the entire world. The investigation begins with a basic question. Was Plato preserving history, reshaping memory, or creating fiction? Before testing locations, the clues must be separated from the mythology built around them later. Plato's dimensions describe an enormous capital and an island larger than many proposed archaeological candidates. The island supposedly held abundant crops, forests, metals, elephants, and a complex network of artificial waterways. Those details imply a large, warm, fertile territory, not merely a small volcanic island. Plato paired the circular capital with a huge engineered plain divided by canals and military districts. Atlantis then attacked the peoples inside the Mediterranean, until an idealized ancient Athens resisted it. This conflict is central to Plato's moral structure: imperial excess against disciplined civic virtue. After moral decline and military defeat, Earthquakes and floods destroy Atlantis in a single terrible day and night. Plato even said, the vanished island left an impassable shoal of mud that blocked navigation. A real candidate must fit many clues at once, not simply resemble one attractive detail. Plato often used invented stories and idealized societies to explore politics, morality, and human failure. Atlantis fits that pattern. A powerful society becomes corrupt, attacks others, and is destroyed by its own excess. Its story functions perfectly, even if no island matching every detail ever existed. But fiction can still borrow from reality, especially in a region shaped by earthquakes, eruptions, and sudden coastal destruction. That possibility leads to the most famous historical candidate, Thera, now called Santorini. Santorini's circular geography, volcanic destruction, and connection to the Minoans make it visually compelling. Yet a volcanic caldera is not the same thing as a city engineered in concentric canals. The Minoan world was wealthy, maritime, artistic, and deeply connected across the eastern Mediterranean. At Akrotiri, volcanic ash preserved a sophisticated Bronze Age town with architecture, trade, and remarkable art. The site offers something Atlantis hunters crave, an advanced settlement abruptly buried by a natural catastrophe. Around the 2nd millennium BCE, Thera produced one of the most powerful eruptions of the ancient Mediterranean. Ash reached far beyond the island, disrupting landscapes, travel, agriculture, and regional life. Caldera collapse and displaced water may also have generated destructive tsunamis across parts of the Aegean. Coastal infrastructure and fleets could have suffered heavily, weakening trade and communication. But the Minoan civilization did not disappear in a single day. It continued for generations after Thera. Plato's stated date is thousands of years earlier than the Bronze Age world of Thera and the Minoans. The chronology is a major problem for identifying Santorini directly with Plato's Atlantis. Santorini is also far smaller than the territory Plato described, and it lies inside the Mediterranean rather than beyond Gibraltar. The theory works best only if Plato altered the date, location, scale, and political story. Thera may have contributed memories of catastrophe without being the literal Atlantis of Plato's text. If Plato's location is taken literally, the search must move beyond Gibraltar into the Atlantic. One group of theories places Atlantis near the Gulf of Cadiz, where earthquakes, tsunamis, and coastal change are real. Remote images have repeatedly produced shapes that look promising, until archaeology demands stronger evidence. Without inscriptions, datable architecture, and a matching settlement, geometry alone cannot identify Atlantis. Another popular theory points to the reshape structure in Mauritania because its rings resemble Plato's city. The resemblance is striking, but the structure is a natural eroded dome far inland and vastly larger than a city. Its circles formed through geology and erosion, not through walls and waterways built by an ancient civilization.
The Azores have also attracted theories because they rise above the mid-Atlantic ridge.
But volcanic islands on oceanic crust are not fragments of a vanished continent, comparable to Plato's enormous island. Modern plate tectonics makes a suddenly sunken Atlantic continent geologically implausible. Atlantis is unproven, but real cities and landscapes have disappeared beneath water. In 373 BCE, the Greek city of Helike was destroyed by earthquake and flooding. Helike demonstrates how a real city can vanish quickly through earthquake, subsidence, and water. Pavlopetri preserves an actual prehistoric town beneath the sea, complete with streets and structures. Many ancient coastal landscapes drowned gradually as global sea level rose after the last ice age. These drowned worlds are real, but they usually vanished over centuries or millennia, not a single night. A credible Atlantis discovery would need a complete archaeological context, not a mysterious shape or isolated artifact. Different disasters leave different evidence: erosion, sediment layers, broken structures, subsidence, and datable occupation. The ocean floor is full of patterns that can imitate walls, roads, pyramids, and harbor shapes. Underwater archaeology must distinguish intentional construction from geology, erosion, and modern material. Geology does not prove whether Plato invented Atlantis, but it rules out many literal interpretations. There is no geological space for a recently vanished continent-sized island between Europe, Africa, and the Americas. Modern bathymetry maps the Atlantic floor in enough detail to reject an enormous sunken landmass. Islands can sink gradually as crust cools, erodes, and subsides, but not as intact empires in a single night. Rapid submergence is possible locally, especially during earthquakes, landslides, or volcanic collapse. A volcanic island can lose enormous volume suddenly, creating memories of land destroyed by the sea. Plato may have combined several familiar kinds of catastrophe into one perfected story. That would explain why parts of Atlantis feel historically plausible, while the complete package remains impossible to locate. The story's political and moral precision may matter more than its geographic precision. If Atlantis was designed as philosophy, searching only the seafloor may miss the point of the story. Atlantis did not remain inside Plato's dialogues. Later centuries repeatedly rebuilt it for new purposes. As ancient texts returned to European readers, Atlantis became a geographic puzzle rather than only a philosophical tale. In the 19th century, writers transformed Atlantis into a lost mother civilization behind Egypt, Mesoamerica, and other cultures. Archaeology does not support the idea that one vanished Atlantic empire created the world's ancient civilizations. Real ancient societies have deep local histories that do not require Atlantis to explain them. Modern esoteric traditions added crystals, advanced energy, psychic powers, and technologies Plato never mentioned. Film, television, novels, and games turned Atlantis into a flexible symbol of lost knowledge. Because the original location is uncertain, Atlantis can be placed almost anywhere imagination needs it. Removing later inventions makes the central problem clearer. Plato is still the only ancient source for the complete story. That does not automatically make Atlantis false, but it sets a very high standard for claiming it has been found. Every proposed Atlantis can now be tested against the same evidence rather than judged by visual resemblance. Santorini fits volcanic disaster and Bronze Age wealth, but fails major chronological and geographic clues. The Gulf of Cadiz fits the western location better, yet no accepted archaeological Atlantis has emerged. The reshape structure looks extraordinary from above, but its geology and archaeology do not match Plato's city. The Azores satisfy the Atlantic imagination more than the geological and archaeological evidence. Most candidates become convincing only when one clue is emphasized and several others are rewritten or ignored. A strong historical identification should make the evidence converge, not require continuous exceptions. No inscription, city plan, datable archive, or archaeological layer has identified a place as Plato's Atlantis. The absence of proof is not proof that every inspiration was invented, but it limits what can honestly be claimed. The most defensible answer may be that Atlantis is philosophy built from recognizable historical fears, and disasters. The problem is not a shortage of possible locations. It is the ease with which almost any circular or submerged feature can be made to resemble the legend. Near the Bahamas, the Bimini Road has often been promoted as an Atlantean structure, despite strong geological explanations for its formation. Regular shapes can emerge naturally when rock fractures along joints and is later exposed by erosion. Yonaguni's terraces look architectural, but geologists can explain much of the structure through layered sandstone, fractures, and erosion. Archaeologists do not identify cities from shape alone. They look for construction methods, occupation layers, tools, pottery, and organized space. Remote sensing is excellent for finding targets, but shadows, resolution limits, and processing can create persuasive illusions. A genuine discovery must preserve relationships between structures, artifacts, sediments, and time. Dating matters because a spectacular ruin from the wrong century cannot be Plato's Atlantis. The location must also fit the travel routes, polydimensionary, political geography, and scale of the original account. An empire powerful enough to challenge the Mediterranean should leave evidence beyond a single later philosophical narrative. When a theory survives only by changing every failed clue, it stops being a testable identification. A useful theory must risk being wrong. Otherwise, every absence becomes hidden proof, and every contradiction becomes part of the mystery. Atlantis survives because it feels both impossible and familiar, a perfect city assembled from real human anxieties. It promises lost knowledge, warns against power, and turns natural disaster into moral judgment. The city vanishes beneath the sea and reappears inside the text that created it. For Plato, Atlantis may have been less a destination than an argument about what societies become. That warning remains understandable, because powerful societies still imagine themselves permanent. The search will continue, because every unexplored coastline and strange formation offers another possibility. But the more evidence this is compared, the harder it becomes to defend one literal lost super-civilization. What remains is still extraordinary, a fictional or reshaped city that became more famous than many real ancient places. Atlantis may never be found, because the complete Atlantis may never have existed outside Plato's narrative. Yet the legend preserves real truths about earthquakes, floods, collapsing powers, and the human fear of losing everything. The most important discovery may not be where Atlantis was, but why people keep needing it to be real. Atlantis remains suspended between memory, philosophy, disaster, and desire. That uncertainty is not a weakness of the legend. It is the reason the legend never stops moving. Atlantis may be history, borrowed memory, philosophical fiction, or some mixture we can no longer separate. What we can say with confidence is simpler. The story is real, the search is real, and the city remains unproven. Beyond the pillars, the map still offers room for imagination. But evidence must decide what becomes history. For now, Atlantis belongs where it began, inside Plato's dialogues, and inside the questions they still create.
The lost city remains lost, not beneath a confirmed sea, but somewhere between ancient catastrophe and the power of a perfect story.
Every compass on Earth depends on an invisible planetary shield generated far beneath our feet. Now imagine north and south slowly trading places across the entire planet. Despite dramatic headlines, a magnetic reversal would not happen during a single frightening night.
Ancient rocks preserve the direction of vanished magnetic fields, like pages in a planetary archive.
A compass does not seek geographic north directly. It aligns with Earth's surrounding magnetic field. That field begins thousands of kilometers below the surface, inside the planet's moving liquid core. Flowing conductive metal, planetary rotation, and heat together operate a vast natural dynamo. Earth's rotation helps chaotic molten motion into structures capable of sustaining magnetism. Heat escaping from the deep interior continually drives convection through the liquid outer core. From that hidden engine, magnetic influence extends tens of thousands of kilometers into space. The magnetosphere deflects much of the solar wind, yet it never blocks every particle.
Auroras appear when guided particles collide with atmospheric gases and release visible light.
Earth's magnetic field has always strengthened, weakened, shifted, and reorganized through geological time.
Scientists reconstruct earlier magnetic behavior by combining evidence from lava, sediments, and fired artifacts. Ocean floor magnetic stripes provide one of the clearest records of repeated polarity reversals. As lava cools, magnetic minerals align and permanently record the field present at that moment. Those alternating bands form a global barcode that tracks long sequences of magnetic change. Reversals are recurring features of Earth's history, although their timing follows no simple schedule. There is no reliable countdown predicting when the next full reversal will begin. Sometimes the field wanders dramatically and recovers without completing a lasting polarity exchange. One famous excursion occurred roughly 41,000 years ago and left widespread geological evidence.
Tiny magnetic particles in sediments can preserve field direction as layers accumulate over time.
Certain iron-rich minerals behave like microscopic compasses while rocks cool or sediments settle. Modern observations show magnetic poles moving because the underlying core flow continually evolves. Small changes in deep fluid motion can alter the field measured at Earth's surface. Most of the time, a large north-south dipole dominates many smaller magnetic features. During a reversal, the global pattern may become weaker, patchier, and more complicated. Real reversals likely involve tangled intermediate fields rather than one clean directional switch. Available evidence suggests full transitions unfold across centuries or millennia, not seconds. After stabilization, a reversed field would remain a functioning planetary magnetic system. Today's civilization uses magnetic conditions for navigation, communication, satellites, and electrical grid planning. A weaker field could expose some satellites to harsher radiation and operational disruptions. Radiation belts respond to magnetic geometry, influencing spacecraft exposure and electronic risk.
Airlines already monitor space weather because polar routes can face increased radiation and communication problems.
High-frequency radio links near the poles can weaken during severe space weather disturbances. Satellite navigation depends on precise timing that disturbed upper atmosphere conditions can degrade. Long electrical networks can collect unwanted currents when magnetic conditions change rapidly. Those induced currents may overheat transformers, distort voltage, and complicate grid control. A pole reversal and a solar storm are different processes, despite frequent online confusion. Electrical hazards depend heavily on how quickly magnetic fields change, not only their absolute strength. A weakened global field could alter how strongly some space weather effects reach technological systems. Greater exposure would not guarantee global collapse, because infrastructure design and preparation strongly influence outcomes. Utilities can reduce vulnerability through monitoring, protective equipment, operational planning, and replacement capacity. Continuous monitoring gives operators warning before many major solar disturbances reach Earth. Some measurements provide only tens of minutes before the strongest magnetic disturbance arrives. Clear procedures can convert limited warning into meaningful protection for vulnerable systems. Even during a weaker magnetic interval, Earth's atmosphere would remain a major radiation barrier. people at ground level would not suddenly receive space-like radiation during a reversal. Life has endured numerous magnetic reversals without a consistent pattern of global biological catastrophe. Many animals detect magnetic information for orientation, migration, or long-distance navigation. Magnetic disruption could challenge some species, yet many combine several navigation systems. Scientists have not found evidence that reversals trigger worldwide animal disorientation or sudden extinction. Instant flip narratives compress a complex geological process into a dramatic but misleading story. Our species experienced major magnetic instability long before modern technology existed. Modern vulnerability comes less from human biology and more from interconnected technological dependence. Failures can spread across connected systems when electricity, timing, and communication services depend on one another. Redundancy prevents a single disruption from becoming a much larger societal emergency. Reasonable emergency planning helps far more than treating magnetic reversal as an approaching doomsday.
Claims that Earth is overdue assume a regular schedule that geological records do not support.
Some polarity intervals lasted briefly, while others continued for tens of millions of years. A long, stable polarity does not mean the underlying dynamo has stopped evolving. Dynamo has stopped evolving.
One notable weak region already affects spacecraft operations over the South Atlantic.
A regional weak spot does not prove that a complete global reversal has begun.
Scientists track magnetic intensity and direction through observatories, surveys, and dedicated space missions.
Global models translate thousands of measurements into updated maps used by navigation systems. Some airports renumber runways when magnetic headings drift far enough from existing labels. Most modern navigation systems can incorporate